Okay, well, we'll get started. So, good evening, everyone. So the purpose of this stream is going to be, exploring the new the PDK that's being released by Google in collaboration with SkyWater and efabless, which is something that has been announced by Tim Ansel a couple of weeks ago, I think. Um, so a little bit about myself, as I just mentioned, I have basically no prior experience in ASIC. So I have something like 15 or even 20 years of experience doing FPGA design and RTL design and that kind of stuff. But I've never done a tape out of an ASIC. Never did anything like that. So take what I say with a grain of salt. If you have better information, or if you know I'm wrong or whatever, don't hesitate to mention it in the chat or correct me. I'm here to basically try and explore this with you tonight, and at least try to provide the little bit of information that I've gathered so far about it. So when this was announced, it was actually announced like a long time ago, like months ago or something. I heard about it, but there were no details, right? So they said they were gonna publish a PDK, and there was basically just this page was available already, but at that time I wasn't especially excited about it, because although it's nice that it's open source and it can provide a great resources. The only tools that were initially mentioned in there were things like Calibre and tools from Mentor and Cadence, which are not open source. You can't possibly buy them. They cost like a fortune, or so. I didn't expect to actually be able to use that. And then, even if I had the tools to actually use the PDK, I wasn't gonna pay for taping out my own test ASIC, like, because it's really not cheap. But then, of course, everything changed when Tim actually did his talk about it, where first he detailed the fact that this PDK is actually going to be compatible with a bunch of open source and free tools, and existing ones are going to get support for this PDK, and new tools and stuff will be written or adapted to work with it, to have a complete tool chain going from like for digital circuit, going from Verilog to the actual tape out. And he also announced that Google was going to sponsor multi-project wafer, where you'll basically get a chance to have your design actually produced, and you get like a few hundreds chip back. Hey, hi to 86 Tech. So obviously at that point that became really interesting, and I started diving into the PDK. So for those who haven't looked at it at all, or who don't even know what the PDK is, it's a process design kit. And so it's basically a bunch of mostly documentation and data files. The kind of stuff you're gonna find in there are design rules, so things like the minimum size of the transistors, and the features of the transistors, the thickness of the metal layers, the number of metal layers, that kind of stuff. Basically, stuff that describes the kind of chip you can produce on that process. It doesn't describe everything in every little detail, so you don't. The fab isn't telling you exactly how they produce the chip, right? But they tell you enough so that you can design a chip, simulate it, and be reasonably confident that what you get back is going to be useful. But they don't detail like every step and every parameters of the process they use to actually produce the chip. So as I said, this will contain like the design rules, which if you look in details, it's stuff like minimum distance, like the minimum, basically it's the equivalent of the track size and track spacing in a PCB, except it's for a bunch of different physical thing on the chip. And we're gonna look at that a little later. Something else you're gonna find in the PDK is pre-made cells. So when you design a digital, what is meant by periphery? Honestly, I have no idea yet. Looking at it, it just seems to be what's outside of the main area, I guess. Yeah, basically anything that's outside this, whatever that is. So yeah, as I said, the PDK will also contain standard cells. When you design synthesize stuff to that process, you don't reinvent the wheel every time. And so they provide what's called standard cell libraries, which is, okay, they tell you, okay, if you want a flip-flop, well, this is exactly how you implement a flip-flop on this process. So you don't have to reinvent it every time, and you can use something that's known working, that has specified behavior and stuff like that. So you don't design, every single transistor by hand, basically. And we're going to look at those cell libraries as well. What else is contained in the PDK is things like simulation models for the transistors. So they basically create the fab, they taped out some test transistors, some test features, stuff like that. They do a bunch of characterization on them, and then they provide you a SPICE simulation model that allows you to know, okay, if you produce a transistor on this process, it's going to behave like that. That kind of stuff. So in the standard cells, I forgot to mention, you have digital cells, but you also have cells like the IOs and stuff like that. A lot of what you will find in the PDK is not actually released yet. So it's not like they did a big dump, a week ago. It's an ongoing process, and every day they're refining and adding new stuff and stuff like that. Yeah, definitely. That's something. So later, I'll actually look at one of the cell and see exactly what's in there. Um, and you also have different libraries depending on what you want. I think it's actually mentioned. Where are the libraries listed in here? Or we can look at them here. So here are the standard cell libraries that have been published so far, and you see there are different variants. And HD means high density. HDLL stands for high density, low leakage. HS is high speed. LS is low speed, but then it's lower leakage. MS is medium speed. There are some that are not published, which are high voltage, which is a cell library that's designed to operate at 3V3 instead of the 1.8 volt core voltage by default on this process. And then inside, oh yeah, you can't see it here. As Eduardo mentioned, inside every cell you have different variant of the cell depending on the drive strength that you need. Because if you're driving like a very long net, you're going to need more output strength, stuff like that. So the SPICE models for the cell do get generated. No, so they're magic. There's a tool that can actually extract SPICE models given a cell. Now, you still need spice models from the fab, because what the tool is going to do is going to see, okay, there is a transistor there, it has this gate length, this gate width, and it will instantiate like a submodel for a transistor of those dimensions, but the actual model for the transistor needs to be provided by the fab. And so if we let's just actually open one of those model. Let me. We're just gonna look at a cell right now. I need to switch scenes. So, well, no, that was actually this. CD Sky130. So I cloned the entire repository, and we're gonna look at the high density cell. So this, we're gonna look at a very simple cell, like a two input AND, for instance, and two. Okay, and so if we look for the SPICE model, so that's the kind of stuff that the that it's gonna extract automatically. It extracts the fact that there is a MOS transistor, and it has this gate width, this gate length, this drain area, this drain periphery, this drain, this source area, this source periphery, and those parameters are going to be used to basically configure a transistor model that's provided by the fab. And here it's called PIVT, which is a IVT PMOS model that needs to be provided by the fab. And that model will be based on experiment and external characterization and stuff like that. Unfortunately, those models have not been released yet as part of the PDK. That's something that should be coming soon in the apparently right after the release the IO cell. They're hoping to release the actual transistor SPICE model, so we can actually simulate this. So that cell was, if I open it in Sky130, let's go to PDK. Wait, libraries, HD, latest cells. So you see, there is a bunch of cells. There is some naming convention. And two. So that's what's provided for each cell. So there is a bunch of file, one that just defines the cell and what it does and stuff like that. Symbol for it, including the power connections, which are important in this case. And they also provide a Verilog simulation model, which I apparently can't open here. Yeah, so you have the symbol without the power connection, and then you have the .pp is the one with the power connection. And then you have also these things where it's basically timing data for that cell. So Eduardo, at the moment I've used ngSpice. I did, yeah, you might have caught it in the here. I did download Zeiss. I haven't actually tried running it, but I definitely wanted to try it because I tried some simulation of RAM and they took forever. And so since this one is supposed to be multi-core, that's definitely something I want to try out. I also want to give a try to CU Spice, which is CUDA optimized Spice compatible simulator, basically. Yeah, have you tried it yourself? I haven't tried it. It does look nice according to like the marketing speech they put on their website, but I yeah, I haven't tried it. So yeah, for each cell, they actually do provide kind of pre-made timing data. I don't know if they're the result of simulation they've already done, or if they're actually or if they've been actually measured. That I don't know. But so at least you don't have to do them yourself. Basically, you can just use the data they provide to gain some time, and you only need to do the simulation if you design your own cells, basically. Okay, good to know, Derek. I mean, it's supposed to be good, especially for large circuits, because it can run them in parallel compared to, like they say, if you have few transistors, you might not get that much benefit because it can't, parallelize as much. But if you have several thousand transistors, then it's starting to be useful. I mean, that's what I read at least. And the same thing for the CUFFT, I think. And so they provide the timing data also for different operating points. You see, you have the fast process corner, which is like the best case at negative 40C and different voltage and stuff like that. And then they also provide, thankfully, like typical performance data. That's for every cell thing you'll find. We can actually take a look at what the cell look like, at the physical level. So far, to do that, I've used KLayout, but I definitely need to try Magic. They're kind of the two main tool, I think, and I think Magic is the more advanced and more capable one, but it has a UI that's not as easy to pick up. I mean, it's basically Tcl from what I've seen. So if we look, let's just me. Yeah, whatever. So I'm gonna open that cell. Open PDK, no, SkyWater, no. SkyWater PDK, libraries, HD, data, cells. And so here there are the different variants that were mentioned by Eduardo that have different strength of output buffer, basically. So we're going to look at the stronger one, for instance, and then we can derive for the other one. And so here you have different files, three files per variation. So the GDS is literally the physical layer that's going to be used for actual production. And LEF is more used by the router to know what to connect where, and so it doesn't have all the details, basically. And so we're gonna just open the GDS here. So that's what the cell look like with all the layers. Thankfully, we do have a file that describes what those layers are. There we go. And so now we have actual names for the layers, which makes interpreting them much easier. So I'm gonna start by hiding all the layer and then just show them sort of one by not one by one, but re-enabling them progressively, because it's a little messy if you don't know how all of that works. Okay, just drink something before I speak a lot. Okay, so let me actually just first introduce the process, because I kind of skipped over that. So what process do we have access to? So it's a 130 nanometer process, and if we look at background information, you have a 5 level of metal, and something it's not mentioned here apparently is that it does have local interconnect layer, and that's what the process stack looks like. You have P-type wafer substrate in which you can make N wells to make your PMOS, basically. You have the gate, which is made of polysilicon, despite being called MOS. It's not metal oxide silicon, it's polysilicon oxide silicon nowadays. And then you have the various layers of interconnect, and so they have this thing called local interconnect, which is slightly different from the other metal. Apparently, so what Tim Edward told me is it's basically a high resistivity metal layer. So I'm not entirely sure which metal. I don't know if it's copper or if it's aluminum for metal 1 to metal 5. But the local interconnect layer is made of titanium nitride, and it has a higher resistivity than the metals. It's lower than the polysilicon layer, but it's higher than the metal, and it's used like inside the cells. It's not used between cells. It's literally just used inside the cells for really short point-to-point interconnect, basically. So that's what our layer stack looks like. And if we look at the cell layout, to produce an actual transistor, an actual cell, what you must provide the fab is literally like the data they're going to use to produce the masks to go through the various steps to actually produce a working transistor, right? So the first step is since it's a complementary, MOS design, like that's what CMOS means, right? Which means you'll have both NMOS and PMOS. So the first thing that's going to be useful is to actually create the N well so that you can put your PMOS transistors. And so that's done using this layer. And so you see, like, you remember the cell, took the entire screen, and basically they put all the PMOS on the top and all the NMOS on the bottom. And so they just create a giant N well in which they're going to create the PMOS. Maybe I'll just quickly draw what the transistors actually look like, in case anyone isn't entirely up to date. Let me switch to this. Okay. So if you want to produce an NMOS transistor, and if you want to produce a PMOS transistor, so you start with so this is simplified, and that's my understanding of it. If any of you know better, please don't hesitate to correct me. So you want to make an NMOS. In this particular process, we start with a P-type wafer. And so the first thing you're going to do is deposit, create the gate. And so you're going to have a very thin layer of oxide created here, which is called the gate oxide, which is really thin. And then above that, you will find the actual gate, which is made of polysilicon. So that creates, one of your terminal of your NMOS. So the first thing is the NMOS is actually, we tend to forget it, right? But it's actually a 4-terminal device. You have the gate, the source, the drain, and then you actually have the bulk connection. Like if you buy a NMOS, in a SOT23 package, you'll usually have the bulk connection being connected to the source. And so you only get 3 terminals. But here, like on the wafer itself, it's a 4-terminal device. And the bulk connection is separate and not tied to the source, basically. And the drain and the source are completely symmetrical. Like you don't see any difference between the drain and the source on the wafer itself. The difference is usually only because you connect the bulk to the source when you buy a device. So that you get your first connection. Then you have your drain and your source, which goes something like this. And those are going to be N plus, so that they are, doped around the gate. And this is going to provide your source, and this is going to provide your drain, for instance. And then you have your bulk connection, which is P plus inside the. So that's sort of what you want to build in the wafer if you want to create an NMOS. If you want a PMOS, it's basically symmetrical, except. Wait, is it? So that's the bulk, basically. Because you start with a P substrate, and that doesn't work to create a PMOS, the first thing, the first step of the process is create a giant zone, basically, of doped with N, which is called the N well, basically. And then you find kind of the opposite, like your bulk connection is going to be N plus, and then you have P plus for the source, P plus for the drain. Bulk. You have the gate oxide, and then you have the gate in polysilicon. So that's what your PMOS looks like. So that's kind of what we're trying to build and describe in the GDS every time we want to create a transistor, right? Just a quick refresher. So let's go back to the GDS. So this zone, which is called N-well, basically determines the opening in the mask where the fab is going to create an N-well for you. So the next thing is going to be creating the gates of all the transistor, and that's done in the poly, which is like polysilicon layer. That's going to be the gate of all the transistors. So this is going to be the gate of all the PMOS because they're above the N-well, and this is going to be the gates of all the NMOS because they're just above the P substrate. So once you've deposited the polysilicon, you need to create the active zone of the transistor, which is the source and the drain. This takes several layers in the GDS to describe that. You first have one that describes where the active zone of your transistor is, and that's this. So this describes where there will be some active zone created. It doesn't actually yet define if that's going to be N plus or P plus. You need a couple of other layers to do that. But something I'd like you to notice here is that even if I hide the gate, that's one continuous zone, right? Even if you look at the drawing here, okay, here. You see the active zone is actually cut. Like there is no P plus under the gate and there is no N plus under the gate here. But on the drawing, this gap is not represented, and it's because the polysilicon is going to be applied first. Even if the opening of the mask go from here to here, when the implantation is going to be going on, all the implants are basically going to be stopped by the gate, and it will create that gap sort of automatically, which is really nice because that also means that gap is going to be automatically aligned with your gate, even if the alignment of your different layers or like photo mask during the production process isn't perfect, your gate will actually always be aligned in in that gap of the MOS channel basically. So if you go back to this, so this determines the active zone, and then you have two more layers which are called PSDM and SDM, and when you combine they basically tell you the active zone if it's P plus or N plus essentially. Why they did it that way and not just have like a one active positive and one active negative layers, but you kind of combine two layers. I think it's just due to the production process and the various masks that they need to produce. I think the first step is basically create an opening for the active region, and then an opening for the active region in the field oxide, and then actually proceed to the implantation. The two different steps of the process basically, and these will represent the actual masks that are going to be used. Among the other interesting layers, there are some layers which are really not that useful to at least understand the cell. I mean, like that's just literally the outline of the cell. That's really not that interesting. But it's gonna be the local interconnect. So you have Lycon 1. So if you go back to this, you see that Lycon is basically what connects the local interconnect to either the active region or to the polysilicon, basically. So that's where you kind of your vias, if you want, if you're thinking in terms of PCB, are, and they will connect between the local interconnect and the bottom layer. And so here is the local interconnect, which I think is like, it's a terrible color, but okay. And this particular cell doesn't have much in terms of metal. You just have the MCON, which is like this, which goes between the local interconnect and the metal one layer, and the actual rails, and these are just power rails, right? So that's the positive supply, and that's ground. And so we can actually start now to analyze how that cell actually works. If we display this, that's the input A, that's input B, and that's the output. So the first thing you can notice is that here the output, which is like this entire thing, is a lot of transistors in parallel, right? You literally have 1, 2, 3, 4 transistors in parallel, just because like that's the _4 variant. And as was mentioned before, that's the to have a high output drive. Like if you're trying to drive a very high fan-out net and reach decent speed, you just put several output transistors in parallel just to drive it stronger, basically, and that takes like a significant amount of the cell. And you can see so you have a transistor basically every time that you have the polysilicon layer that goes over the active area, right? So you have a transistor here which has its output connected to the output, and the other side connected to the power supply. Then you have one here, then you have one here. They kind of reuse the power connection, if you will. And it's symmetric. You have the PMOS side here, you have the NMOS side here, and then here you have the AND gate. And if you draw the diagram of how the transistors are interconnected, you get something like this, right? So this would be so you have a bunch of output transistors in parallel. So these are all the PMOS output transistor, all connected to power. That's your output. And then you have all the NMOS output transistor. So it's kind of your output stage, right? And then if you look, let me switch back to this. If you switch at the input stage, here, so these are NMOSs, right? And that's a ground connection. And then you have basically 2 transistors in series. Like you see, like the active area here, there is no connection to anything else. It goes from the ground through a first NMOS and then directly to a second NMOS, like directly in parallel. There is no connection to anything else. And then that goes to the output. And if you go to the PMOS side, well, they're not in the NMOS are in series, and the PMOS, they're in parallel. You have that's the output here in the middle. And then you have the first transistors that go from power to the output, then the second transistor that goes from power to the output, and the first gate is connected to A, and the gate of the second transistor connected to B. So if we draw that, we have something like A, B. So we have our 2 NMOS in series that go to the output, and then we have our 2 PMOS in parallel. So we have A and B. And so that basically creates an AND, not AND, right? Because if any of A or B is low, then the NMOS, like the series here, is going to be non-conductive, and one of the two PMOS at least is going to conduct, which means that the output is going to be 1. And for the output to be 0, you basically need to be the both PMOS turned off and both NMOS turned on, which means that the two inputs need to be 1. And then you have the output stage, which is an inverter that inverts the signal and also buffers it 4 times to provide like a very high output strength, basically. Hey, hi, Peter. Oh, thank you for hosting. And so the result of that is an AND gate with 2 outputs. And I definitely encourage you to go and look at the various cells. It's very interesting to see how different things are made. There are definitely some pretty complicated, at least, like non-trivial to analyze cell, especially if you start looking at the flip-flops. Let me see if I have so these are the flip-flops, and so if you look at something like this with 2 output layer, let me load layer properties. So that gets complicated pretty quickly, right? You can recognize definitely some structure, like that's the clock buffer and stuff like that, but it's not super trivial. Hey, no problem. No trouble. I actually posted on Twitter. Let me see if I can find it quickly. The response that someone provided. I don't remember the Twitter handle. Ian John Buckley. Okay. So that's I just posted on Twitter like a picture of one of the flip-flops from the standard cell library, and he posted back with the revert schematic of how it actually works and all the transistor and stuff like that. And so that's like I mean, at least I found that super informative to learn how these various things work. Of course, I mean, to be clear, you don't need to go down to that level if you just want to do digital logic synthesis with the PDK, right? You don't need to know to understand how these cells work and stuff like that. But I'd like to be able to design my own or tweak the existing one, that kind of stuff. And so I'm very interested to see how they work. Yeah, exactly. That's my point. Like it's very nice to see how they've been designed and how they work. So these apparently have been made by hand, like somebody kind of like laying out a PCB. They laid out those cells. So the way these are used, in case it might not be obvious, is you take your cell and you basically you glue them one next to each other, right? They really they all have the same height, they just have a different width, and so the power rails will match to the neighboring cell, and so you can literally just glue them in a big line. and then you can also stack them in the other direction, so vertically. But when you stack them vertically, you actually flip it, like you do a vertical inversion, so that, because this is the positive power rail, right? And so you basically want to reuse the positive power rails for the cell above. And so you always have negative, positive, negative, positive, negative, positive, and you just flip that in the other direction, and it doesn't matter in which direction your transistors are built, right? So yeah, that's I hadn't thought of that at the beginning. There is one limitation that I just learned this afternoon, is that all these standard cells, if you look, you will not find any connection to the bulk of the transistor. So I mentioned earlier that the transistor, that the PMOS and NMOS, they're quad terminal device. You have a bulk connection. In the case of NMOS, you need to connect the bulk to the ground, and in case of PMOS, you need to connect it to VDD. You won't find the bulk connection here. There is actually a special cell that's called TAP. So this, for instance, and this cell is like a very small cell, but that handles connecting the bulk connection for the power, and it needs to be placed like periodically. Like if you look in the design rule, it will say, okay, you need one of those cells not more than, I think it's 15 microns away than any of your transistors. Else you will have CMOS latch up. And so it's actually the synthesis and the place and route tools that will need to know, okay, this cell, I need to basically replicate it, put it around the chip and stuff like that, in a way that respect that those connection, basically, because they're not included in the main cell library. Yeah, exactly. for improved flavor. And they're kind of special. If you load the layer, no layer properties. So yeah, I mean, I didn't mention them. There are a bunch of other layers I didn't talk about, because they kind of like very special purpose. Like you have NPC, which is like nitride polycut, which apparently you just need to put there when you have a connection between your polysilicon layer and your titanium nitride layer of the local interconnect. And you have the HVTP layer, which stands for high VT, which is threshold voltage, PMOS. And so I think it's like a sort of a magic tweak that the fab can make to the diffusion layer, to the active area of your PMOS, to raise that threshold voltage. And the process has a bunch of different layers that you can use to tweak the characteristics of the MOSFETs that you get to suit your particular need. Like here, at least in the digital cell library, it's pretty much uniform. They all use the same kind of MOSFET and stuff like that. But I imagine that when there's special implants for like high voltage MOSFETs, because you most likely need a thicker gate oxide, I think. And for a bunch of tweaking analog design and stuff like that, you're gonna need to play with that. Unfortunately, because as I said, we don't have the simulation model of the actual MOSFET, we can't actually be sure of what the influence of those are and if they're important and that kind of stuff. Um, so something I wanted to try is to load one of those cells in Magic, which is something I've never done before, which means I have no idea how to do that, but I guess we'll find out, right? So let's cut it out. It does have an edit mode. I don't remember how to turn it on, but there is one definitely because it offered it to me at some point, and it does some rule checking. But even I'm wondering if even it doesn't use magic in the background for some stuff, because at least when defining the technology library. Oh no, it can export to magic. Never mind, that's something else. Yeah. So the name of the layers, for instance, is currently not in the official repository. Like if you look in the SkyWater PDK, it's not there yet. But Timothy Edwards, which is one of the guy from I think he worked for efabless. I'm not sure actually, but definitely he's a he works for the Open Circuit Design project and does a bunch of open source projects related to circuit design and stuff like that. All of them are going to be used in this flow at least. Yeah, he works for efabless. Yeah, I thought so. I wasn't entirely sure, but yeah. And so he's at the moment, at least on the on the Slack channel for the PDK, he's been mostly the guy answering my questions. And he has a repository named OpenPDK, which contains some files which are not yet merged in the SkyWater PDK release, among which is the layer properties, which contains all the layer names that you can easily load in Kalayote. And it does also have a bunch of stuff for Magic, right? So oh, I think this thing needs to be installed, and I don't. So as I said, I'm discovering that for the first time, so I have no idea how this thing actually works. I will update the checkouts because I think Mitro just pushed some stuff like right before I started streaming. Okay. So yeah, not that much modifications, but still good to take. So well, let's try Magic. So what if I just start it? Okay, it's a good start, I guess. So if any of you know to load a cell in Magic, please don't hesitate to speak up. I think it's GDS open. Doesn't output style set. Read GDS. Okay, let's try that. Let's try to open the same AND gate. Okay, so yeah, I think it needs like the technology file. So something that has been pushed recently to the libraries, which I can't open here. Are these technology files. So it's a file that kind of describes various things like the layers and stuff like that, and more importantly, some of the physical, attributes and DRC rules for those layers, so that all the that's a funny headset. Yeah, it's the only one that was in stock, and it's targeted at fitness instructor. I need to buy like a lapel mag, but at least it seems to be much less noisy than my previous desk microphone that was picking up a lot of the ambient noise. So it contains all the DRC rules and stuff like that that Magic can use to check your design, and some of the physical parameters, like how much current can the trace take, what's the resistivity, what's the capacitance and edge capacitance, and they are basic parameters. Oh, okay. I mean, I can just do this. Yeah, just lower it by like, I don't know, 5 or 10 dB, something like that, in OBS directly. Oh, okay. Yeah, I know the mic is it's pretty hot. Like when compared to other microphone, the output, the voltage output level is pretty high. I can just do this. Okay. And so we probably need to tell Magic how to load that technology file. So if I go back to this open PDK stuff, what other name? Hmm. As I said, all of this, all of the stuff that's in the Open PDK repository is kind of pre-release. It hasn't been officially added yet, so it's not necessarily ready for direct consumption, because like a bunch of those libraries have not been like released yet, which means I can't include them obviously. But I just wanted to load the GDS. It's a pre-program name. So see these like supported device types. That's yeah, I'm running it through a compressor, but that's a software one, and I think that when it clips, it might actually be like the actual hardware input. I might just have the mic too close to me. So yeah, as I said, supported device types are the kind of device that you can build on this process, and for which, if my understanding is correct, the fab is going to provide you a simulation model for. So when we looked at the the spice file, we saw that they used nshorts and they used PIVT because it's a IVT PFET. So now, how do you load this file? Well, no, actually, first, which file are you supposed to load? Sky 130 or Sky 130 file? This one seems much more like final, basically. So can I read a text file? No. Yes. Hmm. So how the hell do you read a GDS file? Yeah, see, that's why I started with layout. It's because it just has like a load GDS command in the menu. Um, it seems to be not that easy with Magic. Yeah, so GDS read doesn't work. It complains about don't know how to read GDS2, nothing in CIF input section of text file, which leads me to believe I need to load the text file first. The question is, how do I do that? Magic, load text file. Oh, okay, so there is technology minimum. Tech manager, okay. So I'm assuming I need to add tech load. Okay, good to know. Let's try that then. Does it have auto completion? Yes. It's gonna open. Okay. So let's retry this. Yes. Perfect. Thank you. And so, unsurprisingly, it looks exactly like the. Like the view in Layout, because well, it's the same cell, right? Um, I'm wondering if you can have layers, Windows. Huh. Yeah. I mean, when I can view it, but I don't know yet how I can like view the layer list or that kind of stuff. I have no idea what I just did. Huh. DRC report, no errors found. Well, that's good news. Yeah, I think that's yeah, definitely. I think you need to basically learn all the keyboard shortcuts and all the TCL command to be able to use this like efficiently. Um, and a bunch of tools actually use it without the UI, like just scripting in TCL. Like I know OpenRAM. Yeah, exactly. I know this is Unix. It's yeah. They actually just script magic to do things like the schematic extraction. Like you provide the cell and it extracts the schematic automatically. Um, that kind of stuff. And unfortunately, if you're not familiar with it, I think this might take some time, right? Um, yeah, I think I'll stop at least my investigation of magic here because this might take more time than I thought to do something useful with it. DRC manager type. Ah, damn it. So 3D viewers, but it apparently doesn't work. I guess I need some dependency or something. Crosshair, maze router. I like just to see the layers. Like, there has to be a way to. I obviously have something here, but even just things like zooming with the scroll, right? That just that doesn't work. So there's zoom out, there's no zoom in. Interesting. Huh. Anyway, something else that I wanted to show off is OpenRAM. So OpenRAM. Yeah, this. Oh yeah, definitely. It's just usually they're meant to so that you can really be very proficient with them with training, like lots of keyboard shortcut, command line, and stuff like that, so that you can get very very productive with them when you're basically doing that all day long. They're not meant to be easy to pick up or anything like that. Yeah, definitely, and I know there will be a lot of learning curve for all those tools basically. Um, yeah, exactly. So in the standard cell library, you find things like AND gate, flip flop, stuff like that, but you won't find like in FPGA you have block RAM, stuff like that. You won't find that in the standard cell library. You need uh, um, macros. Those can sometimes be provided by the fab themselves, like I think in sort of the classic model, you basically ask the fab and they give you a SRAM macro that describes the memory of the size you want and with the sort of the spec you want within what's available to them. But for this PDK, the goal is going to be to use something called OpenRAM, which basically is a project written in Python that you describe the type of SRAM you want, and it generates it for you. It generates the GDS or the layout or the interconnect for you, um, so that you can actually use it. So if we take a quick look at this, Magic says, man, do you want to? Yes, definitely. If we take a look at that, so the first thing I'm going to do is actually switch to the dev branch because I noticed that they have a dev branch which is much more advanced. I've never tried it, but let's live on the edge. Cool. Um, let's open config tests. So you have a Python file where you basically describe the kind of memory you want. So here what I described is a 32-bit wide memory, which I can write 8-bit at a time. And let's make it 1024 words. So it's gonna be a 32 kilobits memory, like 4 kilobytes. Numbanks apparently at the moment is broken, so it doesn't really matter what you put. I'm just gonna disable it for now. And then you can specify what kind of analysis it will do, because it will generate a data sheet for the SRAM you generate. So it will generate, clock to out timing and stuff like that, depending on the configuration that you entered. And it can actually do the simulation at the various process corners, at various voltages, at different temperatures, stuff like that. It will run SPICE and generate all the timing data. It takes absolutely forever. Like I generated like a very small SRAM and did the full ngSpice simulation. It took like 6 hours to generate one timing file. So if I want to generate it for like the various process corners, various voltage, stuff like that, it's probably gonna take the entire week to generate that kind of that kind of data on my workstation. Although it was single-threaded, so this was using ngSpice, and that's why I was investigating other simulators like XYCE which is better at polarization. ngSpice has actually a multi-thread mode, but you need to enable it when you call it. And because OpenRAM calls ngSpice itself, like I can't add options to it. That's something I needed to look at is, can I modify OpenRAM to enable the multi-thread processing, basically? And the other option was like GPU acceleration. Yeah. Okay, well, bye, Gilbert. Thank you for coming. The recording will be put on YouTube, most likely, and I hope you learned something or you enjoyed it. So let's generate one of the RAM here. So at the moment, this does not support the Sky 130 process. They have not published yet the required file, because to generate a SRAM, you can't use the standard cell library, because the standard cell library does not contain SRAM cells. It does not contain some analog modules like the sense amplifiers and stuff like that you find in a SRAM. And so those have to be basically custom designed, integrated into OpenRAM as basic blocks, and then OpenRAM can basically tile them together to make a parametric RAM of whatever size you want. So at the moment, I'm using another process which is supported, which is a much larger process. I think I don't remember which process size that is, but I think it's huge. SCN4M. CMOS layout. There's no details. So Yeah, as far as I know, you really just need to call open RAM and I'm just gonna erase the previous results. So that's pretty straightforward to run. Zoom in. 350 nanometer. Yeah, that's yeah. Thank you. You just run it. It summarizes the configuration you're using and generates a bunch of files for you, basically. I hopefully I've disabled the simulation because else that's gonna take forever. But we can already look at the datasheet that it generated. Oh well, no, sorry, it's not generated yet, of course. So what is it doing at the moment? Interesting. It seems much slower than it was before, but it might be generating more files. I don't think it was generating an LEF before. Okay, so now it generated everything. And so you have a data sheet with some data, which I honestly wouldn't necessarily put much faith into the timing data at the moment because it's just an analytical. So this didn't run ngSpice, right? It just uh, made some assumption and produced some approximative number. Because if I launch the simulation, you wouldn't see the end. But it's nice that it can estimate some things like the power and stuff like that. And if you do the actual simulation, you get all the timing data, including setup times data. You have the clock to out. Um, I'm not entirely sure what operating frequency is because it says you have an operating frequency of 769 megahertz, but then you have like a 6.4 nanoseconds clock to out, which to me sounds like you can't really run it much faster than 150 megahertz or something. So I have no idea what that number comes from and what it means, but you definitely can't use that memory at 769 megahertz. So yeah, to be determined. But now we can actually look at what it generated. So if we look in temp here, it generated all the files. So we've just looked at the HTML, which is like the data sheet. It generated a Liberty lib file, which contains all the timing data in the way that the tools can read and use for system simulation and stuff like that. It generated a SPICE model of all the transistors that I used in the design, and as you can see, there is a shitload of them, which means that's why simulating all of that takes forever. I mean, it's a 32,000 bit memory, right? Each SRAM cell is going to be using at least 6 transistors, I think, plus all the auxiliary logic. So yeah, there's a bunch of transistors in there. It does generate also a Verilog model for your RAM, so you can simulate it in simulation. like in Ivory Log or whatever. This does not include accurate delay simulation. I mean, yeah, it says somewhere, yeah, this delay is arbitrary. Like they put a delay, but it doesn't mean anything. Something to note, though, which is interesting in the kind of RAM that Open RAM generates, is contrary to what you will find in an FPGA. The clock to out is relative to the falling edge of the clock. So the whole logic they implement uses the high period of the clock, so from the rising edge to the falling edge, to pre-charge all the SRAM bit lines, and then does the actual read or write at the falling edge of the clock, which means you basically lose half your clock cycle without even considering the clock to out of actually reading the SRAM, right? So previously we saw that there was a clock to out of like 6 nanoseconds, but really if you're clocking your design and you have a clock period of 20 nanoseconds, 10 nanoseconds is just going to be lost to the pre-charge, because that's half the clock cycle, which is used for pre-charge. And then you are from the falling edge, you still have 6 nanoseconds of clock to out before you can actually read your data. And so you would only have like 4 nanoseconds to do anything with those data before you need to register it again. So that's definitely something to pay attention to. If you're coming from a FPGA, or if you're using an FPGA to simulate your design, that kind of stuff. Yeah. So LVS, I'm honestly not entirely sure what that is. That just looks like a simulation file. I think that might be another sort of reduced SPICE file. Although it doesn't really seem to be that reduced, because it's pretty much the exact same size as this one. Okay, so no, I officially have no idea what the LVS, what the difference between LVS and SP is. Maybe it's explained in the log? SPICE writing, LVS writing. It's possible that one of them is used for the characterization, so that it can generate the datasheet when it runs SPICE by itself, and the other is a SPICE model for you to, as an external user, simulate it. But that, yeah, that'd be my guess at the moment. And so you have the GDS, which is the physical layout, which we're going to look at now with SCA layout, because that's the only thing I know to use. So when you load it by default in layout, as you can see, you don't really see much, and that's because by default it only shows one hierarchy level, but you can show the full hierarchy. Do this, and there you have it. That's your entire SRAM array in all its glory, and you can zoom and you can see all the SRAM cells with all the details and all the metal layers and everything. So the layers that I used in OpenRAM are not the same, or because, as I said, I didn't target the Sky 130 technology because it's not supported at the moment. So I can't load layer names and stuff like that. But that's a SRAM generated for you, and you just have the here. If you zoom, you can. Okay, it's barely readable because Layout is terrible at displaying text, but you have the data output pins here. You'll find the what is that? Actually, can I view top level only? Is that more readable? Well, at least you can see the pins, right? You have D out, all the 32 of them, and then you have the address bits. You only have some address bit here, so the other are somewhere around here, because it obviously split the array into dimension. Like some bits are used to address the rows, some bits are used to address the columns. And then you have the control bin, like write enable and stuff like that. So that's definitely a great tool. I'm very much looking forward to them releasing the Sky130 data for it, because then we can start getting area estimate and stuff like that. That's also something. If you look at the configuration file that you can use, I didn't dig much into the configuration, but you can specify, if you don't want, actually, let me try this. Oh, actually. So you can specify the number of read ports and write ports you want. In the non-dev version, like in the master branch, that wasn't working, that was broken. I don't know if it's fixed in the dev version. Let me actually try that. So no, it doesn't. It doesn't let you do that either. It says bank layout cannot handle more than 2 ports, which is unfortunate, really. It would have been really nice to be able to generate. Oh wait, do I need? That still doesn't work. It would have been really great to be able to generate like a SRAM with 2 read ports and 1 write port, for instance. But at the moment, it's not supported. But maybe that's something we can add support to, because most of the problems and the unsupported features like multiple read points, stuff like that, are Python coding problems. Like they're not the cells they're laid out, they exist. You just need to find a way to organize them in a pattern that you can generate in Python easily. And I guess at the moment they haven't written that for more than 2 port, which is wait, no, it's more than more than 2 ports. Oh yeah. So yeah, definitely something it'd be nice to help with. Something else that that I would like to dig into with Open RAM is adding support for other types of memories. So you have it's meant for generating SRAM, right? Which at the moment is here, but um, internally it has a bunch of Python logic so that you can programmatically repeat a cell and connect it and stuff like that, which mean it might be possible to add support for ROM, like instead of uh, having a SRAM cell at each intersection, you just put a via or no via to a metal layer to mark a 1 or a 0, for instance. And then you can easily encode a ROM and generate a ROM of any size you want. It might be interesting also to see if you can generate memories using the standard cell libraries and using directly flip-flops or latches, which might be smaller, using the Open RAM infrastructure, because you can totally generate, a flip-flop only memory in uses directly, using flip-flops, and it will generate a bunch of flip-flops and all the associated logic, and then you feed it to the automatic placement and routing and stuff like that. But that's a lot of flip-flop to place, and you know that they have a very regular structure, right? So you know how to organize them and route them directly, and so using something like OpenRAM to generate that repetitive structure would probably be much better than just hoping that the auto router is gonna do it for you, basically. So that's definitely something to look into. Among the other tools that are worth because at the moment I haven't actually talked much about how you synthesize. And that's let me gather my thoughts here. Hey, hi, welcome. What was I saying? Yeah, I mostly talked about the content of the PDK and stuff like that. I haven't actually talked much about how you use it to synthesize circuit yet. And the complete flow is designed is going to be something called open road, or rather it's going to be called open lane, which is like this not the fork, but like the specific Sky 130 support for something called open road. Okay, yeah, and so that's a suite of tools that's going to be used to basically go from what did I do? To go from Verilog to actual circuit, basically. Place and routed and everything. And so that includes the just like on a FPGA, that includes several steps. The first one being synthesis, which is taking your Verilog files and mapping them to the instead of mapping them to LUTs. In a FPGA, you map your Verilog to LUT and flip flops. Well, you map them to any cells that you can find in um, in your standard cell library, basically. Um, that's something that's done by USIS as well, well, IBC really. They do have a specific fork of USIS, so you can't just use the same USIS. You have to use the one they provide because it has some specific tweaks and stuff like that. The usage is yeah, it's basically the same. I think I have. Let me see if I can quickly run a design through that. Actually, so again, the open road flow, the official one, isn't published, finalized yet, and stuff like that. I just quickly hacked something together so that I could at least run the synthesis part. So here, if I type, I have the special uses. I need a synthesis script, which I'm not sure what I've done with it. Let me see if I can find it. I know I had one. Yeah, checking the trash. Yeah, I. The thing is, I did some quick early tests and didn't really pay attention where I install stuff and where I put stuff, and then I cleaned everything and just put everything in a Sky130 directory with proper environment and stuff like that, and which mean I might have actually accidentally erased it, but I know I paste binned it at some point because I sent it to Michael Walling, so I must still have the paste bin somewhere. Let me see if I can find it. Mhm. Ah, yeah, here we go. Oh, damn it! I used like a time limited paste bin and it's not available anymore. I'm an idiot. Um, yeah, I'm assuming he still has it. Yeah. But I mean, I know I can. It's not gonna be complete, but I know it's like I didn't invent it from scratch, right? Wait, why can't I click anywhere? Oh, never mind. I basically followed getting started. So one thing I will say is that so far all the tools that are involved are not that hard to install, which is kind of nice. They don't like Magic depends on basically nothing. I mean, you need Tickle TK, but most likely it's already installed. You don't have 150 dependencies to install, including things like JavaScript runtime environment. You just need a C compiler, Tickle TK, a few math libraries, and that's about it. And that's really nice. I mean, here, like in OpenFlow, they do provide Dockerfile if you want to use Docker, but really, it almost doesn't have any dependency. Like you don't need Docker to build users. Like users depends on nothing. So that's definitely a nice change of pace compared to some other projects. Yeah. So what I was looking for, user guide, individual flow steps, logic synthesis. Okay, so that's the synthesis script, which I basically copied. So, oh wait, no, never mind. It's here. That's my synthesis script. It's here. I found it back. Never mind. So I don't need. I don't need to redo it. But let's actually take one of the configuration of, so how it was pi 5 risk 5, I think. Damn it. I don't even remember the name of the project I'm in. Okay, I see your projects. Pi 5 risk, okay. So I'm looking for Vex risk 5 pre-built Verilog file. Damn it. Oh, don't tell me this thing is case sensitive. There we go. So I think that was the most advanced configuration. So let's just take that and try to build it and get some synthesis results from that. So the top level is named Vex Risk 5, if I remember correctly. Okay, no, that's the top level. Use this, import. Oh, wait, no, that's. So here I'm targeting the HD high density cell library, and I'm using the timings for the typical timing. So 25C running at 1.8 volt. I will command out show because it's gonna be taking way too much time. So basically, that's just a script for use this to do synthesis. But really, the thing that matter is that you do the synthesis, the generic synthesis, like you would do normally, and then you can actually provide a Liberty file which describes your cell library, like all the cells that are available, the timing, and what logic function they do, and actually maps your design to it, basically. Now, that is very inexact because that cell library actually contains a bunch of cells that you shouldn't use. But for a first result, it's good enough. It's just playing around here. So what's the command to run a Tcl script? -c. So if we run that Tcl script through uses, right. Of course, it contains black boxes for the SRAMs because they don't exist, which mean I need to define them as being black boxes. Okay, it would have been nice to have some definition for that, but okay, let's. Basically, we must tell users not to touch these and that they will be provided externally, but that requires still writing some stuff. Yeah, I think it can do that, right? Because if you do the memory extraction pass, you will just get like an internal memory cell, which if you don't map it and just define, usually that memory cell would end up being mapped to block RAM, but you could map it to something that just leaves it as is, and then look in the netlist, find all the memory cell, including their configuration, and create an open RAM configuration for them. The problem is not all configuration of RAM that users can generate will work in open RAM. That's the issue, right? Yeah, okay, this is gonna be boring. It should have provided like a Verilog model or something, because I'm just not gonna code them right now. For that, I'm just gonna synthesize the previous one that I made, which basically uses flip-flops. So that's a previous build that I made of the Vex RISC-V, which doesn't use instantiated memory, just infers them. And here they will be inferred as flip-flops actually because, well, because there is no memory. So if I run that, yeah, or try to adapt them because sometimes even if OpenRAM can't generate it directly, you can kind of subdivide the problem into something that's it can generate. But honestly, like a compiler or something I understand absolutely nothing about. I have no idea how uses does what it does basically. I can try to add the memory extraction path here to see if it extracts anything and what kind of parameter they end up as. What's the name of the? So here I run the synthesis, and so you see it basically used a bunch of cells from the cell library, like 68,000 of them, to manage to implement it. And if you look, I mean, I know this processor has a bunch of memory, and you can clearly see that that has been implemented as flip-flops because you have literally 11,000 flip-flops in that design. 8,000 of them are going to be the 1 kilobyte instruction cache. And then the 3 other thousand are the actual CPU, basically. And interestingly, I have no idea how accurate that is, but it does generate like an area estimation. From what is the direct? The thing is, like it uses the internal memories. Like when it extracts a memory, it can generate. It can extract a memory cell that's asynchronous, for instance. That's an asynchronous read port. And OpenRAM just can't generate an asynchronous read memory, which means, well, it's both. Like a bunch of them could be mapped to OpenRAM, but not all of them. That's basically it, right? Well, yeah, not exactly, Tim, because in the case of block RAM, you kind of have fixed. Like the size of each block RAM is fixed, right? Which here it's not. You can dynamically change it depending on what you need. And I have no idea how that works for. I have no idea how Yosis does that. And I wanted to try to see if I can read the run the memory extraction path. So let me. So if I just do. So see here it basically detected Uh, which test? Like the Vex code that I'm using? It's the one in my ICE40 repo. Um, if you go to that's this one. Ah, the test script. Yeah, sure. Oh, wait. How am I gonna paste that in the chat? Uh, because that's actually this is running in an isolated X server, which I don't have access to, and I'm not logged into anything here, which means I can't paste in the chat. I need to basically type it manually. Pastebin.com / bzbvg6rt. Yeah. Oh well, Derek was faster than me. Okay, thank you, Derek. I mean, obviously, you need to edit like which files you read and the name of the top module, and obviously here you need to point that to the actual Liberty libraries for the PDK. If you're synthesizing something small, you can also use the show command here to visualize it, which is pretty interesting. So wait, so here the memory collect path did find all the memories. Collecting memory memorandum minutes. This path goes all the other memory paths in a useful order. Okay. So it has a special path for BRAM. This path converts a multi-port cell into a block RAM instance. This given rule describes the available resources and how they should be used. Yeah, the problem with that path is that yeah, it only supports like specific things. So we need to write like a specific path basically for this. But yeah, definitely that would be definitely convenient to directly write an open run configuration for extracted memories. So if I run the entire memory, generating mem cells, and so if I write ilang I just want to see what those memory cell look like. Damn it. I think it's as a star sign in front. What? Wait, relog, memory, no map, right. Yeah, sure. You could do that. Definitely that would work. I don't know how good that would be though. I mean, you could do a bunch of variation. Like you could generate, I don't know, 4 types of memory, I guess, and I mean 4, 8, whatever, and then use the BRAM path to see what kind of results you get. So I want to get users to write like it's the internal database at this moment, including the internal cells, and it's not doing what I expect. Hmm. Uh, no DAC. I think by default it kind of avoids writing internal cells, but I want it to write internal cells. Hmm. Ah, for fuck's sake. I'm sorry. I'd like to see exactly like the memory cell of fuses, what kind of attribute they have, but yeah, looks like I can't do that. Yeah, something to dig into, but so for the rest of the flow, unfortunately, it's not something I've actually dug into, so I don't know like placement and routing, how that works. I did build the rest of the. Where is my open road? I built the rest of the tools, so the router and stuff like that. I did build them, but they need technology specific things that I don't have. No, I've seen that in Timothy's open PDK repository, there is actually an open lane um, directory, which does contain configuration file and stuff like that, but I haven't looked if if that's complete and if that can be used yet to actually do placement and stuff like that. I'm actually not sure. Like, that's a list of cells. So I mentioned earlier that some of the cells in the standard library, they shouldn't be used for synthesis, basically, because they're not like general purpose things. And it looks to me like there is a lot of these here, and I'm kind of surprised by why. I mean, things like clock buffer. That's something you don't want to use this to infer manually, because to use this, that just looks like an inverter, well, or a buffer. But like a OR2 gate, like why shouldn't it use that? That's what I'm not sure about. Yeah, I know. I know that there are the variants with several output buffer transistor to drive bigger nets and stuff like that. But that's my question: is why? Because as far as I know, like in the synthesis script, so if I understood correctly, this thing, it knows um, the size, and so they have this special path called downsize, buffer upsize, which should, depending on the fan out, automatically bump the striked the. I mean, yeah, it's not impossible, but the synthesis, of course, they're so if currently I'm running Yosis without that no cell configuration, right? And it did seem to produce some somewhat valid result because of those special. Oh, come on, if this ever finishes. Yeah, it's not that fast. Right. Yeah. Yeah. It's possible that it's not correct, of course. But see here, it did. Did it ever use the same cell in different drive strengths? See here, it uses so that's the same cell, and sometimes it uses drive strength 1, sometimes 2, sometimes 4, right? And as far as I understand, that's because it tells ABC to first downsize all the cell to the lowest drive strength, and then selectively buffer and upsize them um, depending on some configuration value somewhere. That was my understanding, because when I didn't do this, like, I'm pretty sure if I actually just gonna command that, and I'm gonna remove the upsize command and rerun the synthesis. Let's see what that yields. But as far as I remember, all the drive strengths are gonna be the minimal one. And apparently I'm wrong. Oh, well, it might be that there's only drive strength 8 for that cell. Well, no, it's... So yeah, okay, I'm wrong. It seems that it didn't do that. Okay. At least something to dig into so that I know exactly what this... why I need this special ABC script and what it does. Because I'm assuming somewhere you need, like, you need to guide ABC some way to tell him, okay, if you have more than that many net, then it might be worth using a different um, more output buffer, because I don't think ABC... it's still they're not using ABC9, so they're using the ABC2, I think. No, the normal ones, which doesn't use timing information, right? So the only thing it knows about the net is the fan out, which means at some point we need to tell him. Actually, I don't know. Is Yosys the one that's gonna decide the drive strength to select based on the fan out, or will the place and route decide the drive strength depending on, okay, maybe that particular output cell, it has um, you know it's driving a lot of net, like 16 of them, but they're all very close to each other, which means that we're not going to have a lot of capacitance compared to, okay, this other cell, we only drive two nets, but there are at the other side of the chip, and we need to drive like a kilometer wide um, metal layer, which is going to have a lot of capacitance. So maybe we need to boost its output capabilities. So yeah, I'm not sure who decides which cell size to use, which drive strength to use, basically. Yeah, as I said, yeah, I have no idea what decision process goes into there. I have to dig into that, because I thought that I understood it with the upsize and downsize thing, but obviously it's not doing what I thought, because if it was, it would be always 1 here. Um, I mean, I guess having like a document, like sort of FAQ, so that we avoid asking the same kind of question. Yeah, like a Etherpad or Google Doc is fine to kind of collect, the kind of interrogation about, okay, how does this work? Like, how are the various pieces fitting together? At some point, once we actually gather enough of those, um, we might be able to write a document that coherently explains things. But at least I know on my part at the moment I don't have like a global vision enough of how all the various pieces fit together to write such a document. I'm definitely, like, all the questions that I'm asking, either to myself and trying to find the answer, or asking on Slack and getting an answer. I'm trying to write them down so that hopefully at some point I know where to fit them in the documentation or stuff like that. But yeah, still too many unknowns to write something coherent basically. But I think collecting them somewhere with the answer would definitely be a good start to get a document that describes kind of the big picture, right? Um, okay, well, I think I'm gonna stop soon because it's kind of getting late here. Unless somebody has some specific question or some specific thing I should be looking at. Yeah, Slack is used that way, but it's sort of hard to find the answer back, right? That's why even if that etherpad possibly includes the question and answer, like you discuss it on Slack and then just quickly add to the Google Docs, okay, what was the question, what was the answer, because I'm pretty sure that some question on Slack are gonna be asked again, just because searching is well, honestly, I'm not a big fan of Slack either, especially the threading model. Like some of the answers are hidden in threads, and so you have to push a button, and I'm pretty sure that some people are missing some answer, some response. And I mean, it's you know, just like IRC or Discord or whatever. It's nice for live interaction, but to collect knowledge, it's not great. Yeah, I mean, it works well for discussion, right? But if you want, oh wait, discourse, that's something else that Discord, right? Discourse, that's like the forum thing. I've never used that, so I have no idea. Yeah, I don't know Discourse, so civilized discussion on the internet. Yeah, good luck with that. Is that what? Yeah, I was gonna ask. That's what you use for the icebreaker forum. Okay. Isn't that what QuickLogic uses as well? Or do they use something else? Oh no, they use PHPBB. Never mind. Yeah, honestly, it's not the icebreaker forum isn't really used all that much, I think. That's kind of the problem. I mean, whatever solution you go with, you kind of guide people to go to them, because I feel that most people will still go to Slack. If Slack is available, most people will go to Slack to ask the question. And then it's fine to have the kind of the live interaction to answer a question on Slack rather than a forum. but then the answer needs to be collected somewhere where it can be found, right? That's the problem. I wouldn't know. I've never been to the KiCad forum, but I've never been. Does KiCad have a Slack channel, or I don't know? I mean, that's kind of too late. There's already a Slack for the PDK. It's already there. It's already populated. People are already on it, so that ship has sailed. And there is also an IRC channel and a Discord channel, and there is another Slack used for Open RAM, and there is a Gitter channel used for Open Road. So yeah, that's fantastic. I used to be only on Discord for the icebreaker, basically, and now I have Discord, IRC, 2 Slacks, and Gitter open. Like half my laptop RAM is used for. Yeah, I mean, I think at this point, yeah, the Slack isn't going anywhere for the PDK, for Open RAM either, because they've been using it for a long time. So yeah, that's not gonna change. Oh yeah, Michael, yeah, there is a mailing list for Pi 5, and there is a Discord channel for Pi 5. Discord server, not just channel. No, direct it isn't, because there is 4, 5, 6, 7, 8, 9, 10, 11. There's like 13 different channels already in the Slack. So you need like 13 IRC channels. Yeah, it's kind of annoying. Like, Discord should just have like a native IRC server, right? Same for Slack. Actually, Slack used to have an IRC server, but that's gone, right? Like previously, you could use an IRC client to connect to Slack, and then it was a server, and so you could just use the various channel in Slack appeared as various channels on that IRC server. Yeah, I think it used to be possible. I think if they removed the option, like Yeah, there you go. Slack is shutting down its whatever. It's IRC gateway. Ending support for IRC. Yeah. Anyway, I think I'm gonna end the stream here, unless anybody else has anything else to suggest that I should check out. I definitely waiting. I'm at least personally. I know I need to dig more into Magic, especially to edit cells and run the various extraction and stuff like that. I'm also impatiently waiting to see what kind of I/O we get and the simulation models for those, so I can run ngSpy stuff like that. Yeah, I mean, there's so many. Basically, I need to check out all the things, right? Because I also want to check OpenRAM, see exactly how that works, and if it's possible to modify to do other kinds of memories. Man, there's so many things. Yeah, too many chats. Definitely. Anyway, guys, yeah, no kidding. Uh, it is. It's definitely a big effort at the moment. As I said, I'm just trying to take it all in and try to see areas where I can help and get somewhere. Thank you. Thank you everyone for joining, and yeah, have a good night too. I don't know if I'm when I'm gonna stream next. I guess when I have something um, interesting to present or show about. Well, about probably still this subject, because I'll be working on that for a while, or maybe actually uh, about the quick logic stuff, S3 stuff, because they've been. So I've been trying to port my USB core to that, and they've been improving the toolchain to at least get it to a point where I can actually achieve that. Anyway, so yeah, follow me on Twitter or follow me on Twitch if you want to know when the next stream is gonna be. Although if you just follow me on Twitch, I guess you get a notification just when I go online, which might be very short notice. Anyway, enough rambling. Goodbye. Thank you everyone for joining, and see you next time.